In 1975, software engineer Fred Brooks observed a counterintuitive reality about building complex systems. Adding manpower to a late software project makes it later. Today, AI engineering is crashing into this exact same paradox. The prevailing assumption in the industry right now is that stringing together multiple large language models, using frameworks like AutoGen or MetaGPT, will linearly scale up reasoning and output. The logic suggests that if one agent is smart, a team of 5 should be 5 times faster and 5 times more capable. Empirical data shows the opposite happens. When tasked with collaborative coding or data analysis, multi-agent teams frequently overwrite each other's work, get trapped in endless communication loops, amplify individual errors, and burn through token budgets without actually advancing the task. Early computing hit this exact bottleneck decades ago. This photograph shows the massive physical scale of mid-century computing, where hardware limitations eventually forced engineers to abandon single, monolithic processors and move to distributed, multi-machine architectures. Modern single-instance LLMs face logical constraints rather than physical ones. They are strictly bounded by context windows, available memory, and token generation speeds. LLM teams operate as strict distributed computing systems. They are bound by the exact same mathematical bottlenecks that plagued early server clusters. To fix an LLM team, we have to treat it like a distributed network. These teams share 4 non-negotiable structural properties with traditional server clusters. First is independence. Look at this network topology model showing 5 distinct agent nodes. Notice the opaque memory boundaries around each one. Every agent operates strictly on its own local context window. None of them have automatic access to a global state. Second is communication. Because they lack a shared brain, these agents coordinate by passing discrete messages, prompts and generated text, back and forth across the network to divide and integrate their work. Third is concurrency. When multiple nodes operate simultaneously on a shared repository, you get synchronization hazards. Agents execute actions based on stale information or silently overwrite a file another agent is currently using. Fourth is fallibility. An agent might hallucinate a variable, stall on an API call, or execute a tool incorrectly. When that node fails, it passes corrupted data to its neighbors, causing the entire pipeline to collapse. Accepting this structural overlap allows us to abandon trial and error prompt engineering. We can apply decades of mathematical systems theory to predict exactly when an LLM team will fail. We can calculate the maximum possible efficiency of an LLM team using Amdahl's law. This principle defines the hard mathematical limit on computational speedup based entirely on the parallelizable fraction of a workload. This chart plots the Amdahl speedup curve. As serial dependencies increase, the curve plateaus aggressively. Researchers tested this on LLM teams. Highly parallel tasks tracked closely along the steep curve, but for highly serial tasks, speedup flatlines. Adding more agents produces zero speedup. Specific models, including GPT 5.2 and Gemini, hit their efficiency plateau well below the theoretical limits. The intrinsic friction of reading and writing messages to coordinate handoffs consumes the time saved by dividing the work. Adding agents to a workflow without analyzing its mathematical parallelizable is a waste of compute resources.
Once a task is parallelizable, you face the primary orchestration trade-off, choosing a centralized architecture where a single controller preassigns tasks, or a decentralized architecture where agents autonomously claim tasks. Decentralization theoretically balances workloads automatically. However, giving agents the autonomy to negotiate their own tasks introduces a severe communication tax. This peer-to-peer network graph illustrates the problem. 2 nodes communicating is simple. Scale to 5 nodes, and the communication lines explode exponentially. Decentralized coordination forces agents into an order of n-squared communication complexity just to figure out who is doing what. This results in idle rounds. In empirical tests, agents get trapped in loops, burning tokens continuously to generate messages confirming they are standing by and waiting for a teammate to finish a dependency. Beyond token waste, autonomous execution on a shared state directly causes consistency conflicts. Decentralized teams exhibit 3 specific types of state violations. They perform concurrent writes, silently overwriting each other's code. They perform rewrites, destroying previously verified work. And they commit temporal violations, attempting to execute a function before its prerequisites exist. Decentralization solves the problem of rigid task distribution, but left unmanaged, it introduces catastrophic communication overhead and silent data corruption. If centralized, pre-assigned orchestration is more token efficient and safer, why ever use decentralized teams? The answer lies in the straggler problem, another concept inherited from distributed systems. In a synchronized phase, overall pipeline progress is gated by the single slowest worker. This bar chart tracks the straggler gap. In a centralized run, rigid assignments mean if one agent stalls, the entire team sits idle. But decentralized architectures mitigate this. Watch the chirp shift as a stalled task is reallocated to a faster agent, reducing time to completion. Evaluating an LLM team on pure wall clock speedup ignores the true operational constraint for production systems, cost efficiency. This table compares the speedup multiplier against the token multiplier across parallel and serial tasks. Because agents constantly synchronize, manage consistency, and negotiate tasks, the token consumption drastically outpaces actual task progression. The red highlight isolates the empirical worst-case scenario, a decentralized team forced to perform a highly serial task. Token usage skyrockets to a 5.8x cost multiplier while delivering a negligible 1.1x speedup. Deploying a multi-agent system is a massive financial liability if the task's mathematical profile does not support the overhead. We can synthesize these empirical results into a strict set of design heuristics. This matrix plots the workflow type on the y-axis, serial versus parallel, against API latency variance on the x-axis. For sequential workflows, the rule is absolute. Never deploy a decentralized team. Rely on a single capable agent or a strict centralized controller to eliminate the overhead. For highly parallel workflows experiencing variable API latency, deploy decentralized teams to absorb the stragglers, but mandate pessimistic file-based locking to physically prevent concurrent write conflicts. Scaling AI requires rigid distributed systems architecture. If you want to build these architectures yourself, check out the Learn by Doing with Steven YouTube channel for hands-on system builds. For deeper discussions on AI systems, subscribe to the Steven Data Talk podcast on Spotify and Apple. Links are in the description.